Watch a beam of light go from the air into a pool of water, and something happens that should bother you more than it does. The light bends. Everybody has seen it. Stick a spoon in a glass of water and the spoon looks broken at the surface. Fine, but ask the question nobody asks. Out of all the possible paths that light could have taken to get from the lamp above the water down to that pebble sitting on the bottom of the pool, it took exactly one. And it happens to be the path that gets there in the shortest possible time. Not the shortest distance, the shortest time. Sit with that for a second. How did the light know? To pick the fastest route, it would seem to need to compare all the routes. It would need to try the lazy path, and the steep path, and the path that goes way off to the left, measure how long each one takes, and then choose the winner. But the light is just leaving the lamp. It hasn't been anywhere yet. It can't have measured anything, and yet it arrives by the one path that beats every other path on the clock, as if it ran the whole race in its head before taking a single step. As if the light knows where it's going to end up before it sets out. As if it knows the future. That is a real puzzle. I want to take it seriously, because the answer is one of the strangest and most beautiful things I know in all of physics, and almost nobody gets told about it. So let's be detectives. Let's not jump to the answer. Let's gather what we actually know, piece by piece, and see where the evidence drags us, even if it drags us somewhere uncomfortable. Here is the first hard fact. Light travels at different speeds in different stuff. In empty space, it goes at about 186,000 miles every second, which is the fastest anything can go. But push it into glass or into water, and it slows down. In water, it dawdles along at about 3/4 of its top speed. This is not a trick. It genuinely takes light longer to cross a foot of water than a foot of air. Remember that, because it is the whole key to the crime. Now the second fact, and this one comes from a clever fellow named Fermat, a lawyer who did mathematics for fun a few hundred years ago. Fermat noticed that you could predict exactly how light bends every single time with one simple rule. Out of all the paths from here to there, light takes the one that takes the least time. That's it. He didn't say least distance. He said least time. And from that one little sentence you can derive the whole law of how light bends when it changes materials. It works perfectly. It has never once been caught being wrong. But a rule that works is not the same as an explanation. A rule tells you what happens. It does not tell you why. And this rule, when you stare at it, is downright spooky. It talks as if the light has a goal, as if the light wants to save time. Light is not a person. It does not own a watch. So what on earth is going on? Let me make the mystery sharper with a little story that has nothing to do with light at all. Picture a lifeguard sitting in her chair on a beach. Out in the water, off to one side, somebody is in trouble and waving. The lifeguard has to get to the swimmer as fast as she possibly can. Every second counts. Now here is the thing about a lifeguard. She runs fast on dry sand, but she swims slow in the water. Everybody is slow in the water. So what's the best path? The straight line, you'd think. A straight line from her chair right to the drowning swimmer. That's the shortest distance. But the shortest distance is not the fastest way, and here's why. A straight line spends a lot of its length in the water where she's slow. She'd be smarter to run a little extra distance on the sand where she's quick, so she can hit the water at a better spot and have less slow swimming to do. But she mustn't overdo it. If she runs way down the beach to get directly across from the swimmer, she's added so much running that she's wasted time anyway. Somewhere in between there is one perfect path. A bend. She runs in a straight line across the sand, hits the water at exactly the right point, and then swims in a straight line to the swimmer. Two straight pieces with a kink at the waterline. And would you believe it? That is precisely, exactly, to the letter, the path that light takes going from air into water. The waterline is the surface. The fast sand is the air. The slow water is the water. Light bends at the surface for the very same reason a smart lifeguard bends her route. To spend less time in the slow stuff. So now we feel pretty clever. We've explained the bending. But hold on, we have not explained anything. We've only made it worse. Because the lifeguard has a brain. She can look at the whole beach, she can think it over, she can plan. The light cannot. The light is dumb. It is not a swimmer with a strategy. So we are right back where we started, only now the mystery has a sharper edge on it. How does a dumb little flash of light pull off a calculation that a trained thinking human being has to concentrate to get right? Let me show you that the trouble is even deeper than it looks, because there's a detail people skip over. When I say light takes the path of least time, that's almost true, but not quite. The honest rule is that light takes the path where the time is what we call stationary, which mostly means least, but sometimes means the most, or a sort of flat spot where shifting the path a hair this way or that way barely changes the time at all. Now, why would nature care about a flat spot in the timing? That is a very peculiar thing to care about. It's the kind of detail that, if you're a detective, makes your ears prick up, because a clue that's strange is usually pointing straight at the answer, if only you knew how to read it. Let's lay out our suspects. One idea. Maybe the light really does send out feelers, little scouts, down every possible path, and they report back, and the light picks the winner. That's a tempting picture. But it's nonsense, and you can prove it's nonsense, because a single particle of light, one photon, the smallest possible dribble of light there is, still obeys the rule perfectly. One lonely photon. There's nothing to send scouts. There's no committee. So scratch that suspect. Second idea. Maybe it's because light is a wave, and waves do clever things. We're getting warmer here. Waves are involved. But the plain old wave picture still leaves you mumbling about the light somehow surveying all of space, and it doesn't tell you why a single photon plays along. So the wave idea is a witness who knows something but won't tell us the whole story yet. We need to lean on this witness harder. And to do that, I have to tell you the most important thing about a photon. The thing that, once you see it, cracks the whole case wide open. Here it is. To figure out where a photon will go, you cannot just track it like a little bullet flying along one path. Instead, you have to do something that sounds completely insane the first time you hear it. You have to consider every possible path the photon could take. Not the straight one, not the bent one, every single one. The path that goes straight there. The path that swerves up to the ceiling first and comes back down. The path that loops around the room 3 times. The ridiculous ones. The lazy ones, all of them. Every imaginable route, from the lamp to the pebble. I can see you frowning. Stay with me, because this is where being a detective pays off. To each one of those paths, every last one, we attach a little arrow. Think of it as a tiny clock hand, a little spinner. As the photon would travel along a given path, this clock hand spins around, very, very fast, like the second hand on a watch gone mad. When the photon reaches the end of that path, the clock hand has stopped at some angle. Maybe it's pointing up, maybe down, maybe sideways. The direction it's pointing depends on how long that particular path is, in time. A longer time path lets the clock spin further before it stops. Now here is the move. To find out how much light actually arrives at the pebble, you take all these millions and millions of little arrows, one for every possible path, and you add them up. Not like ordinary numbers. You add them tip to tail, like laying dominoes end to end, each one pointing in its own direction. You walk along, placing each arrow where the last one ended, following whatever way it points. And wherever you end up at the very end, the length of the line from your starting point to your finishing point, that tells you how much light gets there. So let's do the addition and watch what happens. It's gorgeous. Take the silly paths, the wild, looping, way out of the way paths. A photon path that swings far off to the side takes very different time from its neighbor right next to it. So its clock hand stops at a very different angle than its neighbors. One arrow points north. The next one over points east, the next one south, the next one west. When you lay those arrows tip to tail, they curl around in a little circle and go nowhere. They cancel each other out. For every silly path pointing one way, there's a neighbor pointing the opposite way, and they kill each other. All that wild exploring adds up to almost exactly nothing. The crazy paths erase themselves. Now the path of least time. The fast one. The lifeguard's clever route. Here's the magic. Near that special path, something different happens. Because it sits at the bottom of the timing, at that flat spot I told you to remember, the paths right next to it take almost exactly the same time as it does. Nudge the path a little, the time barely changes. So all the clock hands for that whole bundle of neighboring paths stop at nearly the same angle. They all point the same direction. And when you lay arrows tip to tail that all point the same way, they don't curl up and cancel. They march in a straight line and add up into one big long arrow. They reinforce each other. There's the answer. There's the whole solution to our mystery, and I want you to feel the click of it. The light does not choose the fastest path. The light takes every path, every single one. It really does explore the ridiculous loop and the lazy swerve and the straight shot, all of them at once. But almost all of those paths cancel each other out, because their little clocks point every which way and add up to nothing. The only paths that survive the cancellation, the only ones that add up instead of erasing, are the paths bunched around the one where the time is stationary, around the fastest route. The neighbors agree, so they reinforce. Everywhere else, the neighbors disagree, so they vanish. So when we look, we see light arriving as if it had cleverly picked the speediest path. But it didn't pick anything. It tried everything, and the foolishness all canceled, and what was left standing was the smart route. The cleverness wasn't in the light. The cleverness was in the cancellation. Feel what just happened to our spooky idea. We started terrified that light knows the future, that it scouts ahead and plans its trip. And the truth is almost the opposite. The light has no plan at all. It's the least clever thing imaginable. It blunders down every road there is, like a drunk trying every door in a hallway. It's only because the wrong roads destroy each other so perfectly that what's left looks like a genius found the exit. There is no foresight. There is only addition. Let me circle back to that detail I flagged, the one that should have been bugging you, because now it pays off completely. Remember, I said light doesn't always take the least time. Sometimes it's the most time, sometimes just a flat spot. Now you see why. The rule was never really about least. It was always about that flat spot, that place where neighboring paths take nearly equal time, so their little clocks line up and survive the great cancellation. Least time usually is such a flat spot. But so is greatest time, in a curved mirror. The least was a clue dressed up as the answer. The real culprit was the flat spot, the place of agreement all along. And let me hand you one piece of evidence that this isn't just a story I'm telling to make you feel better. If the light truly does feel out all those paths, including ones a little off to the side, then you ought to be able to catch it in the act. You ought to be able to interfere. Take a mirror, and instead of letting light bounce off the one spot where it should, scrape away most of the mirror and leave only the little patches in the wrong places, the places where the side paths land. By ordinary thinking, light from those wrong patches should cancel and you'd see nothing. But if you space those patches just right, so you remove exactly the ones that were canceling, then suddenly the leftover paths all add up instead. And light comes bouncing off at a crazy angle that no straight line rule would ever allow. We do this. It works. We call the thing a diffraction grating, and it throws a rainbow off a piece of etched metal precisely because the light really was trying all those paths, and we got in there and rigged the cancellation. The shimmer you've seen on the back of a compact disc, those colors crawling around, that is the photon's secret exposed. That is you, looking straight at the proof that light took every path. Let me step back, because I don't want you to lose the size of this thing. We set out to explain a bending beam in a swimming pool, a spoon that looks broken, a tiny everyday nothing. And to explain it honestly, We were forced to say that a single particle of light explores every conceivable route through the universe simultaneously, carrying a spinning clock, and that the world we see is the thin residue left after almost all of those possibilities annihilate one another. That is not a small idea hiding inside a small fact. That is the actual machinery of nature, caught peeking out from behind an ordinary afternoon at the pool. I'll be honest with you, the way a good detective is honest about what's been proven and what hasn't. This adding up of arrows is the genuine way we calculate, and it gives the right answer every time, to more decimal places than almost anything else we can measure. That part is solid as rock. What it means deep down, whether the photon really sails down all those paths in some literal sense, or whether that's just the bookkeeping nature happens to obey, that's a question where honest physicists still scratch their heads and argue. I'm not going to paper over that with pretty words. The arrows work. The story of what's really happening underneath, you're allowed to keep wondering about. I do. But the spooky part, the part that started us off, the part where it seemed light must know the future to choose its path, that's gone now, dissolved completely. The light never knew anything. It never chose anything. It was the dumbest, most thorough explorer in the cosmos, trying every door, and the doors that led nowhere slammed themselves shut by interfering with each other, until only the open one was left. We mistook the leftovers of a vast cancellation for a decision. We saw the survivor and imagined a strategy. So the next time you drop a coin into a fountain and watch it wobble and shimmer under the bent light, I want you to remember what's actually going on down there. That coin is lit by photons that came to it by way of everywhere, by the straight path, and the silly path, and the looping path, and the path that brushed the far wall. All of it, all at once, almost all of it erased, leaving behind the clean bent beam that fooled us for centuries into thinking light was clever. Here's the thing I cannot put down, and I'll leave it with you. We are made of these same particles. The light bouncing off this very page into your eye got there the same way, by trying everything and keeping almost nothing. Which makes me wonder how much of the orderly, sensible world we think we live in is really just the small surviving scrap left over after an unimaginable storm of possibilities canceled themselves into silence. So tell me this. If the path you ended up on is just the one that didn't cancel, how many other paths do you suppose were quietly humming alongside it, the whole way here? Out. There's a second piece of evidence I want to put in front of you, because one clue is a coincidence and two clues is a case. Think about a plain mirror on the wall. Ask where the light bounces. The school book says the angle coming in equals the angle going out, and you bounce off the middle. True enough. But by our arrow rule, the light is testing every point on that mirror. It hits the far left corner, the far right corner, everywhere, and from each spot, a little arrow comes back. Now here's the test. Down near the corners of the mirror, the paths are long, and their times change fast as you slide along, so those arrows spin wildly and cancel, just as we'd expect. But right in the middle, around the proper bounce point, the times go flat, the arrows agree, they add. So far, the arrow rule and the school book agree, which is reassuring but boring. The interesting part is that the arrow rule says the corners are still contributing, faintly. They're just canceling. And if that's true, then I should be able to go to a corner of the mirror where light supposedly never bounces toward you, and by scratching fine lines in just the right spacing, stop the cancellation in that corner alone. And then that dead corner, the part of the mirror that was sending you nothing, lights up and sends light to your eye at an angle the school book swears is impossible. We have done exactly this. The corner obeys. Light bounces off the wrong part of the mirror the instant you stop its paths from canceling. A mirror, it turns out, reflects from everywhere. We only thought it reflected from the middle because everywhere else was busy erasing itself. And I want to push on the timing detail one more turn, because it's the deepest part of the whole business. Why a clock? Why should each path carry a little spinning hand at all? That spinning is tied to the color of the light, which is to say how fast the light wiggles. Red light wiggles slower, its clock spins slower along the path. Blue light wiggles faster, its clock spins faster. And because they spin at different rates, the canceling works out at slightly different places for red than for blue. That is the entire reason a prism splits white light into a rainbow, and the reason the bottom of the pool shimmers with color at its edges. Each color is doing its own separate arrow addition, finding its own surviving path, bending by its own amount. The rainbow is not decoration. The rainbow is each color showing you, in public, where its particular cancellation happened to leave a survivor. Once you see light this way, the colored fringe at the edge of a shadow stops being a curiosity and becomes a confession.